Hello everyone. I am VC Sindhu, a MTech student from IIIT Delhi. I, along with my team members Soumya Jain and Akanksha Sneh, are currently working on this project titled End-to-End Software Prototype of IEEE 802.11 AD, Based JRC Transceiver Architecture, under the guidance of Dr. Shobha Sundar and Dr. Sumit Darak. The main motivation for our work is to enable V2X communications for intelligent transportation system to increase road safety, reduce road congestion, and ensure mobility for all. This demands for data rate of the order of Gbps and latencies below 1 millisecond. Millimeter wave communications have been identified as the only viable approach for V2X communications, since the higher carrier frequencies can support higher bandwidths of the order of 2 to 4 gigahertz and a low fractional bandwidth. This high bandwidth can then support Gbps data rates. But millimeter wave communications have some limitations which have to be addressed before they can become widely used in real world conditions. These links experience very high propagation loss of the order of 10 dB per kilometer due to atmospheric absorption. Thus, they are meant to operate in short range line of sight conditions with highly directional beams. Hence, localization of mobile users has to happen concurrently with communication in order to make millimeter wavelengths viable. There are two approaches in literature to enable rapid beam alignment of millimeter wavelengths. First, channel estimation overheads can be incorporated within the communication protocol to perform localization of the mobile users. However, the algorithmic complexity of this task can result in increased latency and thus reduce the usefulness of the information. The second approach can be adding auxiliary sensors on vehicles, specifically for localizing other vehicles in the environment. However, this approach also has some shortcomings. First, the auxiliary sensor will require additional spectrum apart from the millimeter wavelength. Otherwise, the interference issues will crop up. Secondly, the localization sensors will have to be synchronized with the wireless transceiver at gigahertz frequencies, which is extremely challenging from an engineering perspective. Lastly, the use of auxiliary sensors leads to additional costs in the overall system. So therefore, the solution that has been identified to overcome these challenges is to implement a dual function millimeter wave front end that is capable of both localization and communication. Such a system has the following advantages. First, since a common waveform will be used for both the radar-based localization and communication, there is no requirement for separate spectrum or concerns about interference. Secondly, since the transceiver is essentially dual functional, there are no extra hardware costs or problems of synchronization. This figure represents the JRC architecture, which can be divided into various blocks, namely base station transmitter, base station receiver, mobile user transmitter, and mobile user receiver. The IEEE 802.11 AD-PHY frame structure consists of preamble, header, and data. The preamble, consisting of Gole sequences with the radar functionality, is modulated using pi/2 BPSK and is transmitted as a single carrier type. In the first stage, the data consisting of omnidirectional downlink pilots along with the header is sent using orthogonal frequency division multiplexing, OFDM. The data and header pass through four main stages as shown in this figure. That is, scrambler, LDPC encoder with 3/4 code rate, QPSK modulation, and OFDM modulation, which is an IFFT operation followed by a cyclic prefix addition. The data frame is appended to the header and windowing is performed using raised cosine. This is followed by a digital to analog converter and up converter, which is then fed into RF front end and it is transmitted over the channel. The signal is received at the mobile user receiver, and simultaneously the echo of the signal is reflected back at the base station receiver. The signal transmitted from JRC transmitter, that is at the base station, is also received by the mobile user. Now the down converted signal goes through OFDM demodulation and minimum mean square error channel equalization. Then QPSK demodulation is performed using soft decision approximate log likelihood ratio algorithm, and LDPC decoding is performed with a code rate of 3 by 4. The transmitted bits are recovered after descrambling and the bit error rate is calculated. The receiver block diagram for for the bit recovery is shown in this figure. The reflected signal with two-way propagation is received at the base station receiver and it goes through the down conversion. Now, this down converted radar signal is then explored for the radar based target localization. To enable this, the radar signal processing block after the waveform demodulation is added. This includes extraction of the preamble bits, matched filtering, and Fourier processing blocks shown in this figure, which determine the range and angle of arrival of the mobile user, and music block, which estimates the Doppler velocity of the mobile user. Now, our results show that we can see the plots of range, azimuth, and Doppler for a single point scattered can be seen. And we also have some references of our work. And thank you.